Alright, so we're going to look at mainly evaluating inverse trig functions, and I'm just going to show you a little bit about inverse trig graphs. But we are going to look at sine, cosine, and tangents inverses. And they all have inverses, and so you need to be able to evaluate those, especially for calculus. So to have an inverse function, a function must pass the horizontal line test. And so before we start talking about what the horizontal line test is, let's just look at what some inverses are, and hopefully you remember this from Algebra 2. So what these three things are that I have given you are the original function and a graph of its inverse. And then this line is just the relationship. It shows the relationship between these two things. So if you look at all of three of these graphs, so here's your original function in the red on the second one, and here's your inverse function. Okay, over here, here's your original function, and here's your inverse function. And so if you look at all three of these functions, what do you think the relationship is between the original function and the inverse function? Well, the relationship is just going to be that they are reflections over this line y equals x. And so that just means if you were to fold this graph over this dotted line, they're going to match on both sides. And so all inverse functions have that relationship. And so if you remember back from Algebra 1, in order for a graph to be a function, it has to pass what's called the vertical line test. And so some graphs or some functions don't have inverses, because if we take their inverse, the inverse right here, so this was the original, blue was the original, and so the inverse, when I look at its graph, is not a function because it doesn't pass the horizontal line test. Now these other two would be okay, because they would pass the vertical line test. But this one would not have an inverse because it doesn't pass vertical line test. And so in order for us to not have to look at the graph of the inverse, all we have to do really is just look at the original function, and if it passes the horizontal line test, which means if this line goes through the original function more than once, this graph does not have an inverse. And we could tell that because this is not a function. This one would pass this horizontal line test, even though right here it's kind of got like a little plateau point. It's still only going to touch in one spot. And so this would have an inverse because its inverse would pass the vertical line test. So this passes horizontal line test. This passes horizontal line test. This is going to continually decrease gradually. So it'll pass. And so this inverse will be a function. So in order for a function to have an inverse, it's got to pass a horizontal line test. Now, if we look at sine, cosine, and tangent, if we looked at their entire graph, so let's pretend that this part wasn't dotted, then sine, cosine, nor tangent, if we looked at all of the dotted parts, would ever pass the horizontal line test, which would mean these functions don't have inverses. But we do have inverse functions, and the reason that we do is because we are going to restrict the domain, which basically means we're only going to look at part of the function. So now we restrict the domain for the following reasons. We can use inverses to evaluate, which is the main reason. The second thing is we're going to restrict these functions because the functions won't pass the horizontal line test over the entire domain, which basically means is if we took the whole function is not going to pass horizontal line test, so we just want to look at part of it that will. And then third, the reason that we're going to restrict them like we do, because we're going to look at only certain values for each function, we're going to restrict them so that the function takes on its entire range of values over our restricted domain. And I'll talk more about this in just a second. Alright, so like we said, we're going to restrict the domains for these functions. So if we looked at this sine function, it would definitely not pass horizontal line test if I looked at the whole thing. But if I take only this solid portion right here of this sine function, then that would mean I would restrict this to only looking at negative pi over 2 and pi over 2. And so the reason that we're going to take these specific values, negative pi over 2 to pi over 2, is because our function takes on its full range of values right here. Okay, so from negative 1 to 1, it takes on its full range. And if we only look at this solid portion, it would pass this horizontal line test. So that would mean this function would have an inverse. Same thing with cosine, except we're going to take a different portion of cosine. Okay, so over the solid portion, it's definitely going to pass the horizontal line test. And it still takes on its entire range of values from negative 1 to 1. Tangent is the same way. We're going to only look at this middle cubic looking piece right here and not look at the rest of them because we know it keeps going forever. So that's from negative pi over 2 to pi over 2. And it would pass the horizontal line test on that restriction. So we're going to look at those restrictions. Okay, so for sine, negative pi over 2 to pi over 2. For cosine, 0 to pi. And then for tangent, negative pi over 2 to pi over 2. So then whenever we use these inverse functions to evaluate, I like to think of only looking at part of the unit circle because we know that we use the unit circle to evaluate sine, cosine, and tangent. So I'm only going to look at part of it for these inverse functions. Now, if they ever ask you to find the inverse of something that has a sine or a tangent in it, we said that we were going to restrict those domains to negative pi over 2 to pi over 2 for both of those. So from negative pi over 2 to pi over 2. So I'm going to use this portion of the unit circle. It's kind of like just the right half of it. And so everything stays the exact same on the unit circle. The coordinates, you can see, definitely did not change. And in the first quadrant, the angles are not going to. This is going to still be pi over 6. This is going to be pi over 4. This is going to be pi over 3. And then pi over 2. The only thing that will change, this will still be 0. The only thing that will change is instead of these angles being positive, and so we would go 3 pi over 2 and so forth, now we're going to rotate down in a negative way. And so this is going to be negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. And so I'm just going to label these angles to match our restricted domain for sine and tangent. Now, cosine is really nice because we restricted that from 0 to pi, so basically we're just using the top half of the unit circle here, and so absolutely nothing changes. So I'm going to show you how you're going to use these two diagrams to evaluate. And so when they give you problems to evaluate, they're going to look like this. They could either ask you to find the arc sine or the sine inverse. Now, arc sine, sine inverse, these are the exact same thing. So this is really just saying what is the sine inverse of 1/2. And whenever they ask you for the sine inverse, this, I like to rewrite my problem. This is saying where does the sine, at what angle does the sine equal negative 1/2? Okay, so whenever they ask you for a sine inverse or an arc sine or arc cos, cos inverse, they're basically asking you where does the angle, or at what angle does, since this is sine, what angle does the y equal negative 1/2? And so I'm going to go back over here, and so I'm going to look for where is the y negative 1/2, and that is going to happen at negative pi over 6. So my answer is going to be negative pi over 6 and not 11 pi over 6, because 11 pi over 6 is not in the domain of the sine inverse function. Now, number 2, this is asking me where does the sine equal square root of 3 over 2. So where is the y coordinate positive square root of 3 over 2? So y coordinate is going to be positive square root of 3 over 2 right here at pi over 3. Alright. Third one, this is saying where does the sine, at what angle does the sine equal 2? Well, if I come back over here and look, the y coordinate is never going to be 2. So this answer would just be none. There's no answer. You could say no solution. Because the sign is never going to just be 2. Let's look at some cosine problems. So this is asking me, where does the cosine equal square root of 2 over 2? And so for cosine, I'm going to use the other diagram. I'm going to use this one. And it reminds me of, it's kind of close to Thanksgiving because this is fall. So this kind of reminds me of like a turkey butt. So like turkey feathers here. So I'm looking for where's the x positive square root of 2 over 2. So where's the x coordinate positive square root of 2 over 2? And that's going to be right here at pi over 4. So pi over 4 is my answer. Alright, this one's asking me where does the cosine equal negative 1. So where's the x, cos x? Where is it negative 1? So where is the x coordinate negative 1? That's going to be right here at pi. Alright, so I want you to try some of the rest of these on your own, but I'm going to go ahead and go through them, so if you want to pause it and then come back and watch to check. But this is asking where does the cosine equal negative square root of 3 over 2? So where's the x negative square root of 3 over 2? And that's just going to be right here at 5 pi over 6. So 5 pi over 6 is my answer here. This is saying where does the cosine equal negative 2? So x, where does x equal negative 2? And that's never going to happen. So this is another no solution or none answer. Alright, tangents are a little bit more work, so I'm going to go ahead and write this as where does the tangent equal 0. Now, tangent, remember, is y over x. And so this is saying where does the y over the x equal 0. And so a fraction is only going to equal 0 when the top is 0. So I'm basically just looking for where is y 0 on this diagram, because remember we use this for tangent. So where is the y 0? That's what I'm looking for. Where is y 0? That's going to happen at 0. And so my answer is 0 here. Alright, tangent inverse of square root of 3. This is saying where does the tangent equal square root of 3? So where does the y over the x equal the square root of 3? And this is positive. So when I go look at this, I know that it's not going to be any of these angles down here, because if I put y over x at any of these, this is going to give me a negative answer, and I want a positive square root of 3. So if I look at these 3 angles, that's the only possibilities that I could have. If I put the y over the x here, so if I put 1/2 over square root of 3 over 2, that would mean I would have to flip this and multiply. And then hopefully you could see that this angle would give me square root of 3 over 3, and that's not what I'm looking for. It's definitely not going to be this, because if I put y over the x, that's just going to simplify to 1. But up here, if I put square root of 3 over 2 over 1/2, that would mean I flip 1/2. And that would simplify to square root of 3, which is what I want. So that's going to happen at the angle pi over 3. And so the answer right here would be at pi over 3. And then tangent inverse of negative 1. This is saying where does the tangent equal negative 1? And so tangent's going to be negative 1. It's got to be negative, so it's going to be in one of these quadrants. Remember, we're looking at y over x. And the only time the tangent's going to be 1 is when the y coordinate matches the x coordinate. And so that's going to be right here at negative pi over 4. And so that's how we're going to use the inverses to evaluate problems like this. And so I do just want to show you what the relationship is between the graphs right quick. So this is the graph of the inverse sine function. And so what I've done right here is I've just copied and pasted the original sine function and its domain and range over. And so I want you to look at the relationship between the domain and the range of the sine inverse and the sine function. If we do the sine inverse, the domain of that function, remember domain is from left to right, that's just going to be from negative 1 to 1. And if I look at the range of this function, that's going to be from, this is like negative pi over 2 to pi over 2. And so if you look at these, the only difference is the domain and the range basically just switch. Okay, so that's going to be the same thing for all of these inverse trig functions, and that would be the relationship between their graphs.